Hi. So in this next lesson, we're going to look at atomic spectroscopy. Atomic spectroscopy is another analytical chemistry technique, so it's a technique that's used to analyse various samples in chemistry. And this one is used both to identify which elements are present in a sample, and also it is also able to give us information on the amount of each element in the sample, and it's very, very, very sensitive. It's actually able to detect elements, and particularly metals, down to the parts per million level, so that's milligrams per litre. So it can detect things at very, very low concentration, and that often makes it useful for analysing environmental chemistry type samples, hence why it's in the monitoring the environment topic, but also for in industry and mining and that sort of thing. This atomic spectroscopy, particularly atomic absorption spectroscopy, which is the one we're going to mainly concentrate on, gets used a lot. Let's get into it. So what do we need to know? We need to know about flame tests and how they link into this, and I'll talk about that in a sec. You need to be able to write the electron configuration using subshell notation of an atom or monatomic ion of any of the first 38 elements in the periodic table. I'm actually assuming that you can do that. We've covered that in year 11. If you've got any problems with that, this video here from my year 11 links goes through that. So I'll put this in my playlist, and I'll put this up as a link on Edmodo, so you can find that electron configuration video if you need to remember. And that's that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, all that sort of stuff there. We need to look at absorption and emission. And then we need to get more into the technique of how this is used to analyse samples in atomic absorption spectroscopy. So you're probably familiar with the flame test. I'm sure you've done that at some point. I know I've done that with with some of you this year already. And each element, when we put it into a flame, gives off this characteristic colour. And we'll go through this in detail in a sec, but that's because when we put them into the heat of the flame, it excites the atoms. When the atoms get excited, electrons jump up into higher energy levels. They quickly then relax and come back down, and when they relax, they release light with an energy corresponding to that energy gap of between the electron shells, which the electron jumps back down from. And energy corresponds to colour. So red light has a certain energy, green light has a different energy, purple light has a different energy again. So there's a direct correlation between colour and energy, and also wavelength, which we'll talk about later on. You don't need to know the detail of this, but the reason we see different colours is that light has different energies or different wavelengths. Those things all relate to each other. Let's get into it. So I'll start by talking about emission and absorption spectroscopy. And essentially what happens is if we shine, well, let's do emission spectroscopy first. If we excite this atom here, and this here is a potassium atom, if you look carefully, it's got 20 protons, 20 neutrons, and 20 electrons. And if we apply either some heat or electricity, so we fire electrons, I'll put this in basically a high electric field, so that's heat or electricity, to this atom, what that will make it do is it'll excite the atom. And when the atom gets excited, we can get an electron that jumps up into a higher energy level. So it jumps up till there, then that atom will quickly relax, and when it relaxes, it'll release light, and that light will have the energy that corresponds to the difference in energy of this shell and this shell here. So the third shell and the fourth shell in this very simplified diagram. What that produces when this happens is an emission spectrum down here. So all of these lines of light that we see in the emission spectrum of potassium occur because they correspond to an energy gap somewhere in this atom. Now I've just got the full shells here, I haven't got the subshells, so you can imagine not only have you got these shells here, you've got the subshells of these shells. Then you can also have electrons going into higher energy orbitals or higher energy orbits that aren't currently occupied, but those higher energy ones will also have all unique energies as well. So that's why we get this big range. And potassium having 20 electrons is a reasonably large complex atom, so it has lots and lots of lines in its emission spectrum. Now these emission spectra are unique for every single atom. So if you had potassium or lithium or aluminium or magnesium, all of them would have different energy levels in the atom. Therefore, they would have different lines in their emission spectrum, because basically each of these lines corresponds to an energy level difference here. So that's our emission spectrum. Hopefully it should be a little bit of revision from last year, but I'd expect that you probably need to look at that again. Go back and look at that first video on the previous slide, the Bozeman science video, which gives a really good explanation of emission and absorption spectroscopy as well, if you're still not sure. Now with absorption spectroscopy, it's not quite the opposite, but it's a little bit like the opposite of this. If we shine light onto this atom, so we've got our atom here, and we usually do that squiggly arrow for light, and if we shine some light onto this atom, what can happen is if this light has the same amount of energy that corresponds to one of these gaps, as it goes through, it can cause the atom the electron to jump into a higher energy orbital. So basically we say that puts the electron into an excited state. And when it does that, basically light is lost. So initially we're shining through this light. If some of this light has energy corresponding to this energy gap, it can cause the electron to jump up. That then loses that energy. That energy is then sort of lost. It's given to the electron. And that light doesn't come through. So, we can show, we call these little packets of light what we call photons of light. So 3 photons of light, and if some of those get absorbed, then we won't have as much light come through. So if we had white light here, which contains all the colours, and we shine it through a sample of these potassium atoms, we will get something like this. So white light is made up of all the colours: Roy, G, Biv, red, orange, yellow, green, blue, indigo, violet. And if none of that light was absorbed, we would just get that rainbow type spectrum showing all the colours that make up the white light. However, what we can see is there's these dark bands, and that's because that light has been absorbed by the atoms. And that light is absorbed because it corresponds to the energy level gaps. So we see a series of black bands, and no surprise, these bands here all line up with the emission spectrum. So the same energies that are released when you excite an atom here will be absorbed when you shine white light, which is made up of all wavelengths of light, through a sample. So that's my little summary of emission and absorption spectroscopy. As I said, go back and look at one of those other videos if you're still not really clear on that. So how does that work in an atomic absorption spectrometer, or in atomic absorption spectroscopy? I really encourage you to have a look at a couple of those videos I've got there before, which explain this in more detail. I'm only going to give a fairly brief explanation. But basically, let's say we wanted to analyse for I think, yep, it's there. We wanted to analyse for the amount of zinc in a sample, and I have got zinc there. What we would do is we could use a white light here because that has all wavelengths in it, so it would have the wavelengths that zinc has. But to make this technique work a bit better, we get a lamp here that has a small amount of zinc in it, and when we excite that light, it releases all the wavelengths that are in the zinc atom. Why is that useful? Well, let's say we've got a sample down here, and this sample here has got some zinc in it. This sample is going to get sucked up through this mixing chamber, and we're going to have fuel gas, which is usually acetylene, and oxidizing gas, which is usually oxygen, and they'll all get mixed together in there, and then they'll shoot up here, and this will be lit, so it's in a flame, and you'll get basically all of these zinc atoms will be atomized is the word I'm looking for, which basically just means all the zinc atoms will become sort of individual little zinc atoms floating around in that flame. Now, as this light is coming through from the zinc, if there's no zinc there, all of this light can go through if there's no zinc there. Because only every atom has unique energies, like the orbitals have unique energies. So if there isn't any zinc there, none of the wavelengths of zinc light will get absorbed. However, if there is some zinc there, then some of that light will get absorbed, and we will lose some of that light. So let's now say there was some zinc there. So now we can see so much light goes in. Let's say we've got 3 photons, but some of that gets absorbed, only 1 photon comes out. So from that we can actually work out the absorbance. So it basically goes through a monochromator, which basically just picks out one wavelength. We don't really need to know the detail there, to a detector that's hooked up to a computer, and all of that stuff there, sorry, where's my laser pointer? All of that stuff there works together to give us what we call an absorbance here. So that's a measure of how much light was absorbed. So down here, say, well, this only normally you'd go down to 0 here, and you just pick that up. I just copied this one from a source on the internet. Down here at a low absorption, that's showing not much light was absorbed, so most of it went through. As the absorption gets higher, that's indicating light was absorbed from this side to this side. Yeah, it's been taken out of the sample. So the higher the absorbance, basically indicating the more zinc must have been there that absorbed this zinc light, for lack of a better term. So how do we use this in a practical sense? We'd start by doing a calibration curve. So we would make up known concentrations of zinc. So in this case, a 10, a 20, a 30, a 40, a 50. And we would then run that all through the sample, and we would measure the absorbance for each of those. Then after we'd done that, we'd plot those up on a graph. So we'd plot up that point, that point, that point, that point, and that point. In the old days, we would then draw a line of best fit, or now we would just use a computer to work out basically the formula of that line. And that tells us the relationship between the concentration, if you like, that's like our independent variable that we've controlled and changed here, and our dependent variable here, which is like the absorbance. As we've changed the concentration, we've measured the absorbance. Now, let's say someone brings into our lab a sample and they say, we think this might have some zinc in it, but we're not sure how much. Can you test it for me? So, having done your calibration curve, you then put your unknown sample here into the atomic absorption spectrometer, suck that up, work out the absorption. So let's say we got an absorption of 0.4. We can then go along here, come across from 0.4, then come down to here, and we can go, oh, that must have an absorption of, or that must have a concentration of zinc of probably, what do you reckon that is? 16 parts per million zinc. So that's how we would use an atomic absorption spectrometer to work out the concentration of zinc in an unknown solution. Hopefully that explains how this works. Probably, as I just mentioned before I finish, because every atom has a unique set of energy levels, the presence of other atoms in here shouldn't interfere with it. So if there is some potassium and some iron and some sodium, they would all absorb light at different energy levels, so they shouldn't absorb any of the energy levels that correspond to zinc. So other atoms shouldn't interfere with this, which is one of the reasons that makes this such a powerful technique. It's probably an important point there that I should have made possibly even earlier, but it's a really good spot probably to finish on. So hopefully atomic absorption spectroscopy makes some sense to you now. Thank you.